So the Cholesterol Code documentary just came out. It's focused on the keto diet and lean mass hyperresponders. It's promoted as being grounded in science. Well, let's look at that science. In this video, I'm going through the new KETO-CTA preprint and breaking down its statistical methods. This is the 1-year plaque progression study on lean mass hyperresponders, and it is the main scientific study of the Cholesterol Code documentary. It is important to note that this study hasn't been peer-reviewed, but it has been posted on medRxiv as a full preprint and should be evaluated as a submission-ready scientific manuscript. But this paper has 6 major problems. But please note, I'm not anti-keto, I am just anti-bad statistics, and this study isn't even on the keto diet in general. It's on lean mass hyperresponders on a keto diet. Also, despite the problems, this study is interesting and the dataset could be valuable, and we actually do see some participants with plaque regression. However, it's only over 1 year and we don't know how this will play out long term. That said, problem number 1, they misdefine the main variable used in the statistical models and in the conclusion of the paper. From the paper, their conclusion is neither ApoB nor cumulative LDL-C exposure was predictive of plaque progression. They define LDL-C exposure as baseline LDL-C plus the measured change during follow-up. But change is follow-up minus baseline. So the equation baseline plus follow-up minus baseline just simplifies to follow-up LDL-C. This is not cumulative exposure. It is the LDL-C value measured at the end of the study, and that predicts plaque progression over the previous year. A cumulative exposure should represent LDL-C over time, essentially area under the time curve, typically expressed in milligrams per deciliter years. So calling follow-up LDL-C exposure makes it sound much more rigorous and more informative than it actually is. This raises some questions. The second problem is the charts in the study use a misrepresentation of the IQR that makes the distribution of plaque progression look smaller than the real IQR would show. IQR is the interquartile range, and the standard universally accepted IQR is the interval from the 25th to the 75th percentile, or Q1 to Q3, and it's always reported with the actual Q1 values to the actual Q3 values. About the charts in the paper, they state the red dot illustrates the respective median annual change and its whiskers the interquartile range. But that is not what they plotted. They calculated the median plus or minus half of the IQR, which forces the interval to be symmetric around the median. And that's important because these plaque change distributions are strongly right-skewed with a long upper tail. Their custom calculation drags both limits, Q1 and Q3, downward, making the middle 50% of the plaque progression look lower than it actually is. And they don't even report the Q1 or Q3 values for plaque progression in the summary tables, just the IQR as a single value. This median plus or minus half of the IQR is not a standard metric. Nobody uses this metric. It does not exist. It is not taught anywhere. It doesn't make any sense. And a very important point is that this metric has to be custom programmed. There's no inbuilt function that does this. You can see the problem easily in this chart from the paper, which shows change in percent atheroma volume. There should be 25 data points below the bottom of the red line. There are clearly not 25. And they even use this same fabricated calculation in the retracted JACC paper. And actually that is how I figured this out. Using the raw plaque data from the JACC paper, at first I could not figure out how they constructed those red-shaded IQR bands. But the chart format in this preprint made it easier to see what they had calculated. And once I figured it out, I could reproduce the charts from the JACC paper perfectly. So this is the retracted paper's chart, and this is my recreation of it with the correct IQR shading. Notice how it's not symmetrical around the baseline and year 1. And here it is using the fabricated median plus or minus half of the IQR calculation. It's a perfect reconstruction. And when I figured this out, I said out loud, no, they didn't. They did not do this. I could not believe it. Since this requires an explicit, deliberate custom calculation, as a statistician, I cannot overstate how serious this is. It broke my trust in the entire data analysis, and statistical analysis. And this also raises some serious questions. Problem number 3, they do not report the ApoB models anywhere. ApoB is a central exposure in this study. The supposed lack of association is presented as a major result and repeated in the conclusion. But the actual ApoB model results are not reported anywhere. There's no coefficient reported, no confidence interval reported, no model output anywhere. It's not in the paper's text, it's not in the models table. This is not some minor secondary analysis buried in the supplement. It's one of the paper's main headline findings. I guess it's just another sincere oversight, and a point that is missing some explanations. So the paper states that one revascularization event was confirmed in one subject between scans. So this means that one of the metabolically healthy LMHR participants needed a coronary stent or a bypass during their trial. Of course, we should note that one event cannot establish much about cardiovascular risk, and so while we can't establish much from one data point, it is interesting. But it does matter analytically because revascularization can change the coronary anatomy and affect how plaque is measured at follow-up. But this paper does not explain what procedure occurred, whether the treated vessel or segment was included, whether the participant was excluded from any of the statistical modeling, or how the event affected the plaque analysis. Some places they state n equals 100, some n equals 99, some n equals 95. So which is it and why? When your sample size changes from 100 to 99 to 95, you need to explain exactly who was excluded and why they were excluded. Okay, problem number 4. Their TOST procedure has a basic problem. They apply the same equivalence bounds to regression slopes that measure completely different things. This point is a little technical, but it is very important because they use it to turn "we did not detect an association" into a much stronger claim that the association is effectively 0. So briefly, a TOST, or two one-sided test procedure, requires pre-specified, clinically justified equivalence bounds, or the largest positive or negative effect you would still consider clinically negligible. And those bounds have units, and they depend on the exact regression model units. For example, a slope could represent cubic millimeters of plaque per milligram of ApoB, or percentage points of atheroma volume per unit of LDL-C exposure, or plaque change per day on the ketogenic diet. But they use the same poorly justified negative 0.05 to 0.05 bounds on all the statistical models as though the slopes were interchangeable. They are not. If you don't standardize the slopes, each model requires a separate clinical justification for each bound. And this is not a minor technical disagreement. It is a fundamental misunderstanding of equivalence testing. But it gets worse. Then in the text, they summarize the results this way. Regression slopes were statistically equivalent to 0, with the p-value of less than 0.001 and a 90% confidence interval of 0.00 to 0.00. But which model is that confidence interval from? We don't know. They don't say. And that confidence interval of basically 0 to 0 mathematically cannot correspond to the reported LDL-C exposure model or the ApoB model. My guess is that it comes from a model with a very, very tiny coefficient simply because the predictor is measured in very small units, like, for example, the days on the ketogenic diet model, which means that for every subsequent day, how much more does plaque progress in that one day? But using the reported summary statistics, I was able to calculate the confidence interval for the ApoB and LDL-C models using the baseline values as a stand-in. And from my calculations seen here, the ApoB model would fail equivalence, and the LDL-C model is borderline, but neither one could be rounded anywhere close to 0.00. In my opinion, this is misleading reporting. But wait, we're not done with the TOST problems yet. There's actually an apparent implementation error. So they state that they use the default settings with rule equals classic and CI equals 0.9. The problem is 0.9 is not the default setting. 0.95 is. If you enter 0.95, the default, it produces the standard 90% confidence interval, which they say they ran. But entering 0.9 produces an 80% equivalence interval. And that actually makes equivalence easier to declare. So, just to summarize this section, they used an incoherent equivalence procedure, may have run the wrong and more permissive equivalence test, and then reported an unidentified confidence interval as though it were the main headline models. And this is not a minor technical error. It is a fundamental failure to specify, implement, and report an equivalence procedure correctly and transparently. Okay, problem number 5. They use a post hoc or after-the-fact power calculation to reassure readers that the null or no association LDL-C to plaque finding was not due to low statistical power. But this is widely discouraged in statistics and gets the logic backwards. A post hoc power calculation cannot turn "we failed to detect an effect" into "there was no meaningful effect." And power analysis is mainly for planning a study done prior to the study that helps decide how many participants you need before collecting the data. It is not supposed to be used afterwards to retroactively justify a non-significant result. And even then, their power justification is not transparent. They only show a sample size versus power curve under one fixed assumed effect size, without showing what happens under smaller correlations or less favorable assumptions. This is only one side of the story. And normally you would also show a graph like this, which shows the assumed correlation on the x-axis and the required sample size on the y-axis. For example, if the true correlation or effect size were 0.2, they would need nearly 200 participants, nearly twice the size of the study, for conventional power. So the power justification reassurance does not come from the data. It comes from assumptions they selected after the fact using a method that is widely discouraged. And of course, this also raises some questions. Okay, point number 6, and this is the most important point. So the authors conclude that LDL-C exposure and ApoB were not predictive of plaque progression. However, the models are crude, univariable, simple linear regressions. This is an observational study, and they don't adjust for anything. They run a completely separate model for each input variable, so they do not even adjust for basic confounders like age and sex. These models cannot show that LDL-C exposure or ApoB have no independent, clinically meaningful association with plaque progression. And on top of this, almost every part of the study makes a real association harder to detect. The design weakens the signal. This is a cohort recruited through social media with selection and survivor bias, like a healthy volunteer bias, and there is also no genuine lower or normal LDL comparison group. The LDL-C range is restricted to high and extremely high, and the sample size is small. And the measurements themselves weaken the signal. Follow-up LDL-C is mislabeled as cumulative exposure, plaque progression is measured over only 1 year, and even the authors admit that the measurements have significant noise and variability. And of course, the statistical modeling weakens the signal. The data are skewed. The outcome is noisy change scores, or follow-up minus baseline, which compound error. And the models are crude, inadequately adjusted, simple linear regressions. This is simply a signal weakening pipeline. It's a recipe for producing fragile, no association results, and not real evidence that LDL-C or ApoB do not matter. This is a result based on noise. It is not a true no association result. I strongly think that no clinical or medical decision should be based on these crude, unadjusted, exploratory models. And even then, an author of this study described the finding that LDL-C exposure and ApoB levels were not associated with plaque progression as incredibly robust. This characterization is statistically indefensible and clinically irresponsible. This is not a subtle disagreement over interpretation. It is a basic misunderstanding of no association results. Or it's just spin. For that claim, the design is not robust, the exposure definition is not robust, the measurements are not robust, the statistical modeling is not robust, the null inference is not robust, the reporting is not robust, the interpretation is not robust, and the conclusion is not robust. There's nothing remotely robust about this finding, except the author's insistence that it is. And this definitely raises some serious questions. This study does not meet basic statistical standards, and cannot support the claim that LDL-C exposure or ApoB did not predict plaque progression. The paper's statistical case is a complete shambles. It is fatally flawed, statistically indefensible, and actively misleading. And remember, this is the scientific foundation of the Cholesterol Code documentary, promoted as being grounded in science. Well, This is the kind of science it's grounded in. How do I drop this mic? Boom! Okay, so those are all the major problems with this study. There are, of course, more which we go over in our long 3.5-hour podcast on this study. For example, where they report the rapid plaque progressors in the heart flow analysis as 0%, but elsewhere they report it as 29%. It's actually 29%. And you can also check out our summary video on the previous retracted JACC study, and you might see some patterns emerging there with the statistical analysis.